I did kind of want to briefly address some stuff with acids and bases. I really quickly just threw this slide together, which is why it looks so pretty, all the lovely colors. And it's also why it won't be in your slideshows. Okay? So when we're going through and trying to identify if a compound is an acid or a base, we've got our two primary definitions, which we've already addressed a couple times over now. Your acid is a proton donor. What we said for the sake of this class is we're looking for that hydrogen in front of the formula. If you don't have that hydrogen in front, you're probably not looking at an acid. The one big exception that I can think of is when you look at the NH4 ion, ammonium is technically an acid. Okay? That one's a little bit tricky just because that's set up notationally. Okay? That's kind of the history behind that structure. A lot of the acids and bases that you would work with in general, people understand why they're acids or bases because they've worked with them and they're aware of the structures. You guys aren't aware of how to interpret the structures well enough, or even given the structures for that matter, to be able to do that analysis. Okay? So that's why we went through and said, we'll put that hydrogen in front of the formula as often as I can to signal that we're looking at an acid. Okay? That's not guaranteed. There are some other things that float around. So the ammonium was one. Just happen to think of another one that might show up. Forget where it showed up, but we did see this the other day. This species in the upper left-hand corner. Anybody recognize that one? Also known as, it's acetic acid. The acidic hydrogen in that case is at the end of the structure. Why is it at the end of the structure? It's the oxygen that's actually generating that acidic hydrogen. So what we're trying to show by that version of writing out the formula is something about the structural characteristics. Okay, again, you guys aren't super familiar with how to deal with those structural characteristics, so I'm going to try and prevent that issue from showing up. Okay? So on an exam, if acetic acid was going to show up, the formula that you would see would be this one, okay, the HC2H3O2. Okay? To help kind of clarify that we're looking at an acid. So the acids hopefully are fairly straightforward as far as identifying them. You just look for that hydrogen. If it's there, we got H plus and whatever else is left. Okay? When it comes to the bases are a little bit trickier. Our definition is that they're proton acceptors, and they need to be a source of electrons. So if we're given a structure on its own, what we can do is look for lone pairs. Unfortunately, how do we find lone pair electrons? Have to draw out the Lewis structure to see the lone pairs. Not the easiest thing for you guys to go through and do, particularly because we haven't really discussed how to draw Lewis structures this semester. So we'd be relying on stuff that for some of you may be 1 or 2 years old. Okay, so that's a bit of a challenge. The other thing we could look for would be a source of electrons, so negative charge. Okay? Both of those can be difficult to find. Both of them can be hidden. Okay? So in the case of your most common weak base, you would be looking at NH3. When we look at that, we don't see either a negative charge or a source of electrons. Until you look at the Lewis structure, there's a lone pair on the nitrogen. Hey, now it can act as a base. Okay, so how would you know NH3 acts as a base? We've discussed it now multiple times over. I do expect you to know that NH3 is a base. That's pretty much the only weak base that you'll deal with, okay, or the tricky one as far as I'm concerned. The other options would be, and since we started with this, let's just roll with acetate. Okay. Would acetate ion be a base? Yes? How do you know? See that negative charge. Right? So the negative charge would suggest a base. How could we hide that from you? Not quite put an H in front, but right idea. we could put any group 1 metal or other metals for that matter in front. Okay, now we don't see that negative charge as obviously, and now everything goes crazy. Okay, nobody knows what's happening anymore. Except what's one of the things that we've discussed when it comes to your group 1 metals? They completely dissociate off of it, and we don't have to worry about it. So if you see that there, you can immediately flag that as saying that the sodium ion isn't there and that we're looking at the acetate ion. Okay? Which kind of brings us back to the quiz when we're given each of these formulas and we add them to water. So the acids, hopefully, everybody's fairly confident with. Yes, no? Okay, some yeses. Good enough. The bases were a lot trickier. Particularly, we looked at that copper hydroxide. Okay, and that one ended up being a whole lot more difficult than I had anticipated. Okay, and the more I thought about it, the more I realized where I think that big difference came in. We're looking at copper, which is known as classified as a metal. Hydroxide is complex ion. What bond occurs between a complex ion and a metal? An ionic bond. What happens to ionic bonds in water? They dissociate. Okay? They may dissociate to varying extents, but they will dissociate. Which means, if we're going to predict this reaction, we're going to see copper ion and hydroxide. Okay? Depending on your skill level and interpretation of this, I wouldn't expect you to go too far with this. We might balance this more appropriately as saying 2 hydroxide. Okay? The other option that I would accept, at least for this problem, where we've only released one of those hydroxide ions. Okay? What you're responsible for recognizing is that that is a metal and a non-metal complex. That is an ionic bond that dissociates into the ions. Okay? Based on what you guys ended up writing or what I ended up seeing, a lot of people are just jamming hydrogen onto that structure. Okay? So you saw the hydroxide, but instead of splitting it into the ions, you immediately just started jamming stuff onto it. Okay? With your weak bases, or bases in general, a lot of them will have to dissociate first. So go through that initial dissociation. Okay? So if you see that metal, split it up into the ions. Ideally, you would split it up completely. And then evaluate. So if we split that, what do we have, an acid or a base? Base, how do you know it's a base? We see OH minus. Okay. Where else can this kind of come into play, or where we saw issues before, is if we then tried to react each of these ions with water. Okay, we could go through and react. Yeah, this one's going to be a little bit weird with that copper. Copper plus water, we'd get copper hydroxide and, what was that? Hydrogen ion, H plus. The other one, which is really the one I wanted to look at, if we take OH minus and we react that with water, that is still showing up on there, isn't it? Yeah. A lot of people have problems with this one too. Which is the reactive species, water or hydroxide? Why hydroxide? It's the most charged species there. How do we stabilize the hydroxide? What makes it unstable? Negatively charged. So to make it more stable, we have to make it more neutral. What does it need to neutralize? It needs a positive, so we can look to our water molecule and identify a positive. What's the positive in our water molecule? Hydrogen ion. So we generate, and what's left over are OH minus. Okay. Yes, that looks a bit weird. Why? You get the exact same thing on both sides. Okay, so this is one thing that kind of makes bases nice. If you see hydroxide, when it reacts with water, all it's going to do is generate more hydroxide, okay, in the exact equal amount, which is why we don't have to go through and do all sorts of other propagation techniques to see how it affects the pH. We've already hit where it affects the pH. If you see hydroxide, what happens to your pH? Goes up or down, or doesn't stay, or doesn't change. Goes up because we're becoming more basic, because we see hydroxide ion. Okay? Kind of help with those. So hopefully now when you go through and try and, if you attempt to rework these problems, you should be able to do those a little bit easier. I'll leave you guys to decide if it is easier or not. Okay? The next part was the flip side. The very first question was what, question 3, 4? Question 3. We already walked through that one yesterday, so I'm not going to walk through that one again. The next sequence of questions is ultimately asking what I've got up here. We want to know the concentrations of, and I expanded this, oxalate ion, hydrogen oxalate, oxalic acid, and hydrogen ion in a 1 molar solution of oxalic acid. Given 2 pKa's. Why are there 2 pKa's? When we add oxalic acid to water, what happens? We get, whoops, good call on the hydronium. We get hydronium, and why do we stop at hydrogen oxalate? Why not take it all the way to oxalic acid, or sorry, oxalate? Why do we only remove 1 hydrogen?
Because it takes a certain amount of energy to take the first hydrogen off.
It takes varying energies or effort to remove each hydrogen. So we want to evaluate the removal of each hydrogen at each individual stage. So we can now go through and look at the equilibrium expression for this removal. Okay? That would be the first removal of an acidic hydrogen. So we might refer to that equilibrium as K A, because it's an acid, and this happens to be the first hydrogen removal, so we'll use 1. What happens with hydrogen oxalate? What's special about hydrogen oxalate? There's a couple things there. It is a base because it's negatively charged, and it's also an acid. How do you know it's also an acid? It has that hydrogen in front of it. So if we go through, and now that we've generated this hydrogen oxalate, we're still in a water solution, what happens? It can then react with water to generate, whoops, be consistent, more hydrogen ion and the oxalate ion. If we look at the equilibrium expression for this, using symbols, we would say this is K for our equilibrium. Is this an acid or a base reaction? How do you know it's an acid reaction? We see the H plus in our product, or hydronium ion. Okay? This happens to be associated with oxalic acid. Okay? Because where did we get the hydrogen oxalate from? Oxalic acid. Okay? So this species is intricately related to this, but it happens to be the removal of the second hydrogen. So instead of just calling it Ka, we call it Ka2. Okay? So how is all of this important? Well, as soon as we add hydrogen, can't get any of the words right. As soon as we add oxalic acid to water, it reacts with water. In the process of doing that, it generates hydrogen ion and hydrogen oxalate. Great. So we could determine the concentration of that hydrogen oxalate and that hydrogen ion. However, hydrogen oxalate, as soon as it hits the water, also reacts to generate more acid and oxalate ion. So just by adding a polyprotic acid to water, we've drastically increased difficulty, that works, increased the difficulty of our problem. We have to evaluate 2 equilibrium expressions to go through and total everything up. Okay? And that's what 4 and 5 we're looking at. So when you went through and did number 4, all I said was for this very first equation. You'll notice I didn't call it Ka1. I just said pKa. Why? Because at that point, the only questions I asked about were the things in that first equilibrium expression. When we move to 5, 4, I don't even know what the number is anymore. When we move to question 5, I now asked about the oxalate ion. The oxalate had to come from the hydrogen oxalate, which means we're looking at a new Ka value. So if you look at the pKa for that problem, did the number change? It went from 1.25 in question 4 to 4.14 in question 5. It absolutely did change. We're looking at a different reaction coming or stemming from the same source. Okay? So to go through and answer this problem, to get the concentration of oxalate, we only have to solve with our very first expression. Okay? Just our Ka1. Because that's the only place where our oxalic acid shows up. So to get the oxalic acid, let me try that again. Start with oxalic acid. To get its concentration, I only need to solve the very first expression. Okay? Because that's the only place it shows up. To get the concentration of hydrogen oxalate, yes, I need to solve the first expression. Okay? Because it increases there. But what happens in the second expression? It decreases. So to get the concentration of hydrogen oxalate in that solution, I must go through and solve for Ka1 and then also solve for Ka2. Because I increase and decrease, I have to account for that difference. So that means 2 ice charts. To get the oxalic acid, God, to get the oxalate ion, our C2O4, okay, the very last species, what expressions do I need to solve? Why do I have to solve both? Because it only shows up in the second expression. Why do I have to solve both? I would have to know the concentration of this. To get the concentration of the hydrogen oxalate, what did I have to do? Solve for the first one. Okay? So beginning to end for this problem, we've got a lot of steps to go through. It's technically 2 ice charts to go through as we've seen it before. Okay? The last thing is the hydrogen ion. Hydrogen ion is generated in the first step. It's also generated in the second step, which means to get the concentration of hydrogen ion, I must solve both expressions. Okay? Again, the long way. So in theory, you guys went through and did this. If you take a look at those sequence of questions, 4, 5, and 6, they are all related to each other intentionally. The answer for 4, the concentration of hydrogen oxalate, what did you get? 0.052. It's a good answer. That's what you should have gotten. That's what I got. Take a look at question number 5. What concentration of hydrogen oxalate are you starting with? 0.052, the exact same number. And that's because these problems are tied. We're ultimately solving this one question. I've just broken it into each of the individual steps. Okay? When you go through and solve this, assuming I did this right, these were the answers you should have got, I believe. Oxalate ion, 0.048, roughly. Your hydrogen oxalate, looks like I propagated out way too many sig figs on this. Effectively 0.052. Our oxalic acid, we get 7.24, 10 to the minus 5 molar. And the hydrogen ion, we get our 0.052. Okay? Did anybody notice any interesting patterns pop out of this? Yeah.
Oxalic acid, well, your pKa ended up equaling your X.
Close.
Or not your Ka, rather.
Your Ka. So when we look at the concentration of our oxalic acid, 7.24 times 10 to the minus 5, to generate the oxalic acid, that should say oxalate. I got those.
Yeah.
Man, no wonder I'm getting them confused. Oxalate. Okay, to get our concentration of the oxalate ion, okay, our 7.24. Okay, to solve for that, what expression did we need to use? We needed the equilibrium constant with respect to acid for step 2, which means we would use pKa 2. We'd have to convert our pKa 2 into a Ka to use it. How do we convert our pKa into a Ka? Okay. To get our Ka, it's going to be 10 to the negative 4.14. What's that number equal? 7.24 times 10 to the minus 5. Interesting. Concentration of oxalate ion is the Ka for that step. Okay, so that's kind of a neat little result. That whole second ice chart to figure out the concentration of oxalate ion. Did we need to do that at all? No. All that effort you spent in generating that and writing that out, that big space of paper, all you needed to write was that the oxalate ion equaled 10 to the negative 4.14. Done. Works for every single polyprotic acid out there. Okay? So if we wanted to figure out the concentration of, so let's say we started with sulfuric acid, and I want to know the concentration of sulfate ion in that solution. Okay, to get that sulfate ion, I would need to look at the Ka for step 2. Okay, or I could go through and solve all the way from the Ka of step 1 to give me the hydrogen sulfate, to then go through and solve for the sulfate ion using Ka2. What's the concentration of sulfate ion going to be? This is a fun one. Everybody wants to give me a number. Stop giving me numbers. I've actually already given you the answer. What's the answer? Ka2. Okay? No math. We already know the answer. Okay? And that has to do with all of the approximations that we put into our reactions. Okay? And as long as we get a big enough difference between the concentration that we start with and our Ka, we're good. Okay? So your Connect homework goes through and does a couple problems along these lines as well. Okay? So that's one big lesson that we can pick up out of this. We don't have to solve all the way through. Yes? We haven't gotten to 6 yet, but we're right about there. So to get the pH, any questions about this first? Okay, so the next part of it is taking a look at your hydrogen ion concentration. Did anybody notice anything interesting about our hydrogen ion concentration? If we looked at our reactions, we started with, let's make sure this actually stands out. We started with our oxalic acid, which was our H2C2O4, drawing the shorthand version. Whoops. Generates our hydrogen oxalate, and our hydrogen oxalate then generates H plus C2O4 minus 2. So to figure out our pH, we need to know the concentration of the hydrogen ion. Well, hydrogen ion is generated in 2 spots. So we would have to add these two to get our total hydrogen ion concentration. So that sounds kind of crappy. We'd still have to go through and solve 2 ice charts. Okay? Well, let's go back through. What was the hydrogen ion concentration generated in the first step? The answer is technically up there, though it's not obvious. 0.052. How do you know that? Because the concentration of these two should be relatively close to the same. There we go. Okay, so it comes out roughly the same. We then go through the second step, and we generate more hydrogen ion. How much hydrogen ion did we generate there? How much did we generate in that second step? So it's a different question than how much is there at the end. That's our 7.24 times 10 to the minus 5. We could add those up, take the negative log. Great. What do we get for a pH? 1.28. Okay, cool. So we went through, solved the long way. Awesome. We got a pH. What would happen if instead of going through and adding that all up, I said, you know what, I'm really, really lazy. I'm tired of doing these ice charts. I'm just going to take this one. Take the negative log of 0.052. What do you get? 1.28. Interesting. What does that mean? The amount of hydrogen ion generated in subsequent steps is not enough to contribute to our overall hydrogen ion concentration. So to solve for our pH for a polyprotic acid, all we have to do, is solve for the very first step. Each subsequent step is not going to add enough hydrogen ion to actually increase our pH enough, or sorry, decrease the pH. Okay? So it doesn't contribute. So we get 2 kind of shortcuts that come out of polyprotic acids. We do still have to solve the very first ice chart, okay? Because that's the only way that we can get our concentration of the hydrogen oxalate. It's the only way we can get our concentration of hydrogen ion. Okay? But after that first ice chart, we can then skip steps. Our hydrogen ion concentration in that total solution is only going to come from that first step. Okay? Every other contribution of hydrogen ion is so small at that point that it doesn't contribute. So we don't have to worry about calculating it, unless you really, really want to, which by all means, go ahead and do so. Okay? The other thing that we learn is that our conjugate base, our final conjugate base, once we've removed all of our hydrogen ions, is equal to the Ka for the step that generated it. Again, we don't have to solve an ice chart to follow that. Okay? So it's kind of nice. 2 little shortcuts when it comes to polyprotic acids. If you don't like shortcuts, which at this point I don't blame you, then solve these entirely, all the way through, every single ice chart. Worst case, it's good experience. The intent behind this quiz was to make you go through and solve it all and then get irritated that there were so many shortcuts that you didn't have to do all this work. If I get you irritated enough that there are shortcuts, what are you going to do with the shortcuts? You're going to remember them and actually use them. If I just tell you they're shortcuts from the get-go, you'll forget them, you won't use them, and you do poorly on the test. Okay? Kind of makes sense? Anybody irritated with that yet? How many of you are going to remember the shortcuts? Okay, there we go. A couple people. It's good enough. Okay, the very last question. There's a couple different ways to solve that last question. It says, what happens to the pH when we add oxalate or potassium oxalate? So the first thing we would do, what does potassium oxalate look like? On an exam, do I expect you to be able to take the name into the structure or the formula? No, I'll give that to you. Okay, I don't expect you to have nomenclature memorized. So that's our formula, potassium oxalate. What happens when we add that into water? We've got a metal and complex ion, so it completely dissociates. would be our very first step. We'd get 2K plus and our C2O4 minus 2. What does the K plus do? Absolutely nothing, because it's a group 1 metal. We don't have to worry about it, so that's nice. Okay. What does the oxalate ion do? How do you know it acts as a base? All sorts of fun answers on this one. Doing the long one right here. Negatively charged, which means it acts as a base. Okay, so let's go back to the question before I even start drawing out equations. Okay, if we've got oxalate and we add it to water, what's going to happen to the pH? If it acts as a base, what happens to pH when you add base? Becomes basic, which means the pH goes up. Okay, no problem solving, nothing at all, just basics on it. Okay, we could go through and look at equations. We could generate HC2O4 minus 1. And what would the other species be? OH minus. So in the process of adding oxalate to water, what do we generate? We generate base. What happens to the pH if we have an increased concentration of hydroxide? pH goes up. Okay? So a problem can look very misleading. In this case, it's easier than it may be made out to believe. Okay? So being able to identify from the formula whether you have an acid or a base will allow you to predict what happens to the pH when you add it, okay, to any individual reaction. Okay? Questions about that? Okay, like I said, make sure we get that quiz by the end of today. Now what we're going to do is kind of move into Chapter 16. Chapter 16 looks at buffers, titrations, and solubility. Okay? Pretty much this entire chapter is all math. Okay? There isn't really any way to get around that, so you got to be careful with that. I assigned a very minimal amount of work to go through and do this. Okay? These problems, more than any other, take a lot of time and a lot of care when you go through and deal with the numbers. So please be careful, solve multiple problems to get that practice. You'll need it for the exam. Okay? So the first thing I want to do is actually look at what's known as a titration curve. So we're going to start with oxalic acid. Okay? So what happens to the pH, or what would I expect for the pH if I had oxalic acid? What should the pH value be? What is oxalic acid? An acid or a base? How do you know it's an acid? There's an H in front and I said acid. Okay? So take advantage of that. Where should your pH be? High or low? Low. So let's go ahead and say we start with oxalic acid, nice low pH. Now what I'm going to start to do is add base. Okay, so let's draw out a reaction here. H2C2O4 goes to H plus, C2O4, whoops, HC2O4 minus. I add base. Okay, in this case I'm adding a strong base. What should happen to the pH? Should go up because we're adding base. Okay? What is that base going to immediately do? It's going to take hydrogens. Where is there a hydrogen in this reaction? On the product side. So we add one molecule of base. What happens? It cancels out that one. Are we at equilibrium anymore? No, because there's no product. So what happens? To re-achieve equilibrium, a second molecule of our oxalic acid dissociates to form hydrogen ion. So yes, we added base. We would expect our pH to go up, but does it go up by that much? I still see hydrogen ion. Okay, so we're no longer at equilibrium once we've added that. So another molecule of C2O4 comes along, makes another H+. Okay, so yes, the pH does go up, but it's not going to go up by a huge amount. Okay, because I still have that acid present. Okay, so we might go up a little bit. Okay, and what we'll notice is that it will actually stay relatively level. Okay, it's still going to gradually increase because we're gradually removing that hydrogen ion. We are still adding base, but it's not going to change drastically as long as this species is here to feed more hydrogen ions to replace the ones that are being consumed. Okay? Eventually what happens? I add enough hydroxide that I completely remove the hydrogen from this species, which means now when I add a little bit more hydroxide, pH goes from being acidic to basic. So we would expect a big jump. I didn't leave myself a lot of space here. We would expect a pretty big jump in our pH value. Okay? Then what happens? What is present at that point? Okay, we do have hydroxide. Is there anything else present at that point? Is it oxalate? Look at our balanced equation so far. Our oxalic acid generated hydrogen oxalate. We don't have oxalate. What happened? What is present? Hydrogen oxalate. So at that point, I have now hydrogen oxalate. What does that hydrogen oxalate do in water? Dissociates into H plus and oxalate. So our pH will spike, but it won't go basic quite yet because the hydrogen oxalate has a second hydrogen to give up. So what ends up happening? Now when I add more base, it reacts with this H plus, but I've now destroyed my equilibrium, and now this guy generates more. So what happens to my pH again? It's going to level off again. Whoops, it should still increase. Then what happens? I continue to add OH minus until I now remove all of the hydrogens from here. What happens to the pH? It's again going to spike. Might as well spike through everything else. Okay. Eventually, we will see the pH level off. Why should it level off? Because we can't add any more hydroxide ion to the solution. Okay. There's an upper threshold of hydroxide ion in our solution, so we would expect it to level again. Okay. So at that point, somewhere on that up curve, the reaction that we're now looking at is C2O4 minus 2. Okay. It doesn't have any more hydrogen ions, so that when I try and add base to it, this can't stabilize that base. Okay, so pH just continues to spike. Okay, so what we've got now is this kind of general curve. So we want to kind of address some interesting points on this. What can you tell me about the blue dot? What happened at that blue dot, roughly? What's that? No more oxalic acid, which really means that the moles of my oxalic acid equal, yes, we could say 0, but we can relate that to something else. What did you say? Not quite at that point either. What reacted with the oxalic acid to make sure it went away? Hydroxide. At that point, my initial moles, we should add that I guess, the initial moles of our oxalic acid equal the moles of hydroxide. Seems rather simple, but why is that important? I now know the initial moles of oxalic acid I started with. So if I didn't know the molarity of my solution, I could now determine it. Okay, so that's kind of nice. What about the green point? Ultimately the same idea. At that green point, I know the moles of my C2O4 minus 2 equal the initial moles of H2C2O4. And we could say also the moles of NaOH to go from blue to green. Okay? So all we're trying to identify is what things are changing, where we're at with different positions. So if I went back and said, right here, this black point, what species is present primarily at that back? Let's shift the black point down a little bit. What species is primarily present at that point? Hydrogen oxalate. How do you know it's hydrogen oxalate? It's between our transition from when we've got rid of all of our oxalic acid to getting rid of all of our hydrogen oxalate. So we can start to identify little pieces off of this curve and try and interpret things. Okay? These titration curves become even more important when we go through to try and determine what's happening in that system, okay, in each of our flat sections. What is happening to our pH in this region? Does it change? No, it doesn't. So we come up with a fancy word for that. What fancy word do we use? Begins with a B. Buffer. What we've done is buffered that solution to that pH so that when we add base to it, what happens to the pH? Nothing really changes. So we stay at a relatively constant pH. So these buffer ideas or these buffer solutions are extremely important as far as biology or most reactions go. Why? To control the pH. Why is that important? What happens if we change the concentration of hydrogen ion when we did the EDTA titration? That's for those of you in lab. Your readings change. Hydrogen ion was part of the balanced equation. If we change that pH, that can potentially change our reaction. What happens if we did that with our starch reaction, the rate law? If we didn't have a buffer system there, hydrogen ion was again important in that reaction. So if we didn't maintain the pH within a very narrow range, what happens? All the chemistry goes out the window. So that just goes back to what we're doing in our lab. What happens if we look at our blood? What pH is our blood? Was it 7.4? Someone said that? It sounded pretty accurate. Relatively neutral. What happens if our pH of our blood gets too high or low? We die. Okay. Ultimately, why do you die? All of the proteins in DNA, all of those particular systems are built around a very particular pH, how they interact with their environment. If we change the pH, we change those interactions. So if we have a protein that's all nice and folded up and we change how it interacts with the rest of the environment, what's that protein going to do? It's going to change its shape. Well, if it changes its shape, okay, imagine a keyhole. Try to go into your door. Okay, if the lock changed its shape every so often, how often are you going to be able to get into your house? Okay, you're going to stick the key in and it's not going to work anymore. Okay, so when we're looking at pHs and buffer systems, that's the main reason why a lot of biological systems are based on very narrow pH ranges. So biology has generated buffer systems. What's the buffer solution that we end up using in our bloodstream? Primary one? I'm not positive on this one. I think I'm right, though. Bicarbonate. Okay? We use that as a buffer for our pH bloodstream so that we maintain a relatively neutral pH. Nothing changes too drastically. What happens if the pH changes drastically, particularly with carbonate? This is an interesting one, actually. So let's take all of the possible phases for our carbonate. Whoops. Anybody know anything interesting about H2CO3 or carbonic acid? Highly reactive how? Decomposes into H2O and CO2. If your bloodstream gets too acidic, what happens? So as we add acid, acid comes in, reacts with this basic species to generate this one. If we continue to add acid, what happens? We generate this one. Now what happens? Decomposes into CO2 and water. Why is that helpful? What do you think the pH is around your lungs? High or low? Probably low. Why? We're trying to expel CO2 out of our lungs. So if we want to biologically push CO2 out of our bloodstream, what can we do? Increase the acidity around the lungs. What happens? Our buffer system reacts with the hydrogen, or reacts with the acid around our lungs, generates carbonic acid. We can now push CO2 out of our bloodstream. What about near, not our lungs, anywhere else in the body? What would we expect of our pH there? Do we want CO2 being released into our muscles? No. So what would we expect of the pH? We would expect it to be higher so that we're pushed more towards this end of our buffer system. If we push too far out of balance, our blood pH gets too acidic, we end up generating CO2 everywhere in our bloodstream, which ends up happening, or ends up doing what to us? We suffocate. Okay? We end up generating too much CO2, we don't get the oxygen that we need, and we end up dying. Okay? So these buffer systems and how they buffer and react is really important to what we're actually dealing with. Okay? Unfortunately, where does that importance really come into play? Just what we talked through and walked through. Very rarely do we have to deal with specific numbers that are causing all these. Where's that rare case where we have to deal with those numbers? This class. Lucky you. Okay? So keep that in mind when you're going through and looking at these systems. What we're trying to do is evaluate pretty much the biological impact of that. So we can look at other types of systems that buffer. And they're going to buffer around their pKa, which we're, let's see, did I put that on the next slide? Trying to think how I want to do this. Yep. This is another one of those you're going to be irritated at me, but I'm used to that. So, what we'll do now is kind of look at a buffer example. To be a buffer, we have to have the concentrations of our conjugate partners. If we don't have both conjugate partners present, when we add something, it's going to change our pH. So for instance, if we go all the way back, okay, and if we looked at our oxalic acid, we had this general curve, right? Okay. In this spot, or in either of these spots, we've buffered the pH. The pH doesn't change that much in that particular range. What happens when we push outside of that range? Does the pH change? Yeah. So we're no longer acting as a useful buffer. Okay? What does that mean? Well, if I take a look at dead center in either of those spots, what happens when I add base? Which way does the pH go? It goes up ever so slightly. What happens if I add acid? The pH goes down ever so slightly. And that's because at that position, so for the bottom one, we have H2, in this case, we have our oxalic acid in equilibrium with our hydrogen oxalate. So when we add base, yes, it removes the hydrogen ion and our pH goes up a little bit. What happens when we add acid? The acid, to buffer, we would hope our pH doesn't drop drastically. So if I just add straight H+, what would I expect to happen to my concentration of hydrogen ion? Looks to me like it doubles. That looks a pretty huge change in our pH. Does it actually double? What does the acid tend to react with? Something basic, something potentially highlighted or underlined in red. Now with a box. So what happens when we add the acid? That excess acid puts a strain on the equilibrium. So the acid then reacts with our conjugate base, and what happens? We remove it. We turn into H2C2O4, our oxalic acid. Okay? So when we're adding our strong acids and bases, we have to see how they directly impact our reaction. Okay? And that may require doing some extra calculations on top of just doing or evaluating our equilibrium. So that when we add acid in this case, yes, it reacts with this, so we've increased the H+ a little bit, but then we remove it by converting it into oxalic acid. That removal mitigates the drop in pH, so it stays relatively constant. What happens if we see a sharp drop? What does it mean if the pH sharply drops here at the end? There's a lot of hydrogen ions and none of this. So to have a buffer, we have to have both these species. This one will buffer our acid concentration. The presence of our acid will buffer our base. So we need to have both conjugate partners present. If we only have one, then it doesn't completely buffer, because I can add something else to cause it to shift. For instance, if I only have oxalic acid present, what happens when I add more acid? There's now nothing left to react with the acid that I've added. What happens to pH? It drops sharply, because there's nothing to mitigate that extra addition. Okay? Kind of makes sense? So your buffers are only valid when you have both partners. As soon as you lose one or the other, you're going to see a sharp either rise or drop, depending on your perspective in the pH. That sharp change is no longer a buffer. Remember, the buffer minimizes that change. Okay? So what could we go through and do? Well, we could evaluate all the way through this. So we'll look at kind of, this is ultimately a combination of all three things up there at the top. Ion effects, buffers, and titrations. We're doing all of them. Okay? So we could go through and determine the pH of a 1 liter solution that is 0.1 molar in sodium fluoride. Okay? The Ka for this is 6.8 times 10 to the minus 4. Okay? Anybody notice any problems? Where would you start? Let's try that. Okay, I like the converting to Kb, but you actually looked further ahead than most people would, I presume. Might be helpful to look at a balanced equation first. What did we start with? We started with sodium fluoride. When we add that to water, what do we get? We get sodium ion and fluoride ion. Okay, immediately, completely dissociates. How do you know it completely dissociates? Because it's sodium. Is sodium going to affect our pH? No. So let's ignore sodium altogether, and instead of looking at that equation, what we want to do is see how fluoride interacts with water. So we'll draw a new equation where we've got our fluoride plus water. What happens? Fluoride is a base. How do you know it's a base? It's negatively charged, so it becomes HF. It needs to accept that hydrogen ion. What's left over? OH minus. One thing that can be helpful, and I know I've pushed drawing out the equilibrium expression way late in the process of solving these, and I'm starting to regret that because I'm noticing a lot of people are drawing it out incorrectly. So let's draw out our equilibrium expression first. K equals what? Our products over our reactants. Why do we not show water? It's a liquid, so we assume its concentration doesn't change enough. What type of K did we just solve for? What type of K did we just solve for? I don't care what the question says. What K did we just draw? KB. So when we go through to try and solve our ice chart, what do we need? We need the KB. What are we given? Ka. So if we're going to go through and solve our ice chart for our concentrations, we need to make sure that we convert that Ka over to a Kb. Okay? As far as the rest of setting this up, go through it relatively quickly. We won't worry about water. What was our initial fluoride? 0.1 molar. We didn't have to worry about any kind of weird conversions on that. It was just given directly to us. What's our initial concentration of HF and OH minus? 0. Okay. What we're assuming is we take the fluoride ion, immediately dissolve it into water, and we say, don't react. Okay, now react. Okay. So the initial system is 0 for both of those. What happens in our change? Or if we push all the way back to chapter 14, what's our Q going to be?
0.
What's the relationship between Q and K? Q is by definition going to be less than K, which means products form. We shift towards the right. Those need to be positive. This needs to be negative. How much do they change by? X. Do we have to worry about coefficients? That was kind of a mean question. Yes, we have to worry about coefficients. Why are we not that stressed about it? Because they're all 1. Okay, we still do have to worry about the coefficients. It just happens they're all 1. Okay, what's our equilibrium? 0.1 minus x, x, and x. We could now go through and solve or substitute into our K expression, which is something I would highly recommend you also do stepwise. So it's x times x divided by 0.1 minus x. To solve, we need to know the Kb. What is the Kb? Kb equals the Kw over the Ka. Was it minus 4? Quick look at the numbers is going to suggest that the assumption will work in this case. And you should be able to get an x value. Is there questions? I'm seeing some quizzical looks. What's the question? Did I write something wrong?
Just right after the x times x.
Yes.
10 times what's that?
10 to the negative 14. I know. I was afraid you were going to comment on that.
How did we get that again?
10 to the negative 14 is what?
Something constant.
The Kw.
Oh, okay.
So to solve for the Kb, it's Kw over the Ka, because Ka times Kb.
So we're assuming it is at 20.
We're assuming at that temperature, yep. Okay. The assumption should work, and we would get x equaling, run that by me again?
1.47 times 10 to the negative 11. Is it 10 to the
Did you square root? I'm hearing a couple people saying no. What are the other people saying is the answer? Too many numbers. Seth, what do you have?
I got 1.2 things.
Okay. What is X equal to? Okay, sorry. What is X stand for? Not the number. What does it represent? The concentration of OH minus.